Thanks, Meredith. Thanks, Meredith. I'm happy to introduce our speaker, Louise Farquharson, who is with us from the University of Alaska Fairbanks, where she is currently an assistant research professor. And her background is in quaternary permafrost studies, but she sort of is a jack of all trades, studies geomorphology, and has done a lot of remote sensing work as well. But her current research interests examine the permafrost thaw, coastal dynamics, drained lake basin dynamics, and permafrost affected landscapes. Some of her recent work has begun to explore how permafrost degradation and coastal change are impacting communities. And today we are pleased to invite her to speak about not so permanent permafrost, novel subaerial talik development across the discontinuous permafrost zone of Alaska. So I'll hand it over to you, Louise. And thanks for joining
Miriam.
us.
Yeah, thanks for inviting me to talk today, and thanks to everybody for turning up to listen. Hoping that we can have a pretty interesting discussion about this data. And so, yeah, as Maria mentioned, I'll be discussing novel subaerial talik development in the discontinuous permafrost zone in Alaska today. And this work is very much a collaborative effort, working with my colleagues at the GI Permafrost Lab. So the data I'll present today will be a combination of observed temperature data from boreholes, and that analysis is primarily done by myself and Alexander Kolodov, and then some modeling efforts led by Vlad Romanovsky and Dmitry Nikolsky using the GIPL permafrost model. I also want to mention that this the data that I'll discuss is funded by NSF as part of the Arctic Observation Network. The award number is down here in the bottom right. Next slide, please, Liz. So starting with the basics, what is a talik? So a talik is ground in an area of permafrost that remains unfrozen all year round. And you can see this little block diagram here from the nice classic textbook by Hugh French, The Periglacial Environment, which shows different types of subaerial permafrost that we can have. And so we can see that there are super permafrost taliks, which is where we have talik forming above the permafrost but below the active layer. We can have intra-permafrost talik, which is where talik is sandwiched within the permafrost, and sub-permafrost talik, which is beneath the permafrost. And today I'll be primarily focusing on super permafrost talik in subaerial, so that means not underwater, but under areas of vegetation. And next slide, please. And for the most part, I think, if you're familiar with the term talik, it's probably in the context, or it's most likely to be in the context of thaw lakes. And so thaw lakes are known to be big emitters of carbon, and one of the primary mechanisms of carbon release from thaw or thermokarst lakes, deep thermokarst lakes, is the formation of taliks below the water body. And so you can see in this figure from Walter Anthony's work in 2018 in Nature Communications, they explored carbon emissions from lakes and compared it to adjacent terrain that was not affected by lakes. And they found that, lakes were emitting a lot more carbon than the adjacent tundra landscape. Next slide. And so you can see, if we start to consider taliks forming subaerially instead of subaqueously, i.e. under vegetation rather than under lakes, we have to start thinking about how this could impact carbon emissions on a landscape scale. Next slide. So I don't have any carbon data to present, but this is kind of one of the topics that I think that might be worth discussing after the slides is, what implications widespread subaerial talik has for carbon cycling in the Arctic and subarctic. Next slide, please. So this map shows a range of our borehole locations. Those are all boreholes that are installed and maintained as part of the Arctic Observation Network project. And and they're distributed. We also have sites within the continuous permafrost zone too, but none of them exhibited signs of talik formation. So we focus primarily on the discontinuous zone. So you can see here, each dot basically represents a different borehole, and the color of each borehole corresponds to its current thermal state. So the blue sites are where we still have permafrost. The gray, the browny green sites, there are two of those where we had pre-existing taliks from the start of our observation period. And the orange dots show where we have recent talik formation. So 25 of these sites out of 56, and then 11 sites where we had no permafrost. And you can see what's interesting here is that the distribution ranges quite far north. So some of the talik sites are quite close to the continuous permafrost zone boundary. And just to emphasize that these sites are all subaerial, so areas of vegetation, not lakes. They're undisturbed, so they're not impacted by fire or human disturbance. They're all driven by changes in air temperature and to some degree snow as well. Next slide, please. So to place this kind of in more of a temporal context, this table shows us all the sites on that previous map that were orange. And so what we see here is a table showing our observation period. So the earliest observations we have are from 1995, that range through to 2021. As you can probably expect, our data collection over the last this summer and last summer has been a little spotty due to COVID and restrictions on fieldwork, understandably. But we have some pretty solid data from 95 through to 2019. And then we have a list of the different sites where we have these observations from. And so gray means that we weren't observing at that borehole at that time. Blue means that we were observing ground temperature and that permafrost was present. Orange shows that talik has begun to form, and green shows that we have a talik that has then refrozen. And so what's interesting to see in this table, firstly, is that there are sites where we've had many, many years of consistent permafrost presence and then talik formation, and that this talik formation can be either persistent, or we can have talik forming year after year, or it can be intermittent. So some of these sites, you can see that the ground has refrozen after initial talik formation. So we're in a period of time right now where talik formation is occurring, but in some locations it is still intermittent. Okay, next slide, please. Another thing to note about the range of sites that we have is that they span quite a wide range of vegetation types. So on the left-hand side here is an example from Bonanza Creek in the Fairbanks area, which is a black spruce forest. And it's an area characterized by quite a thick organic layer composed of mosses and sedges. And on the right-hand side is an example of our council site near Nome on the Third Peninsula, which is characterized by shrub tundra. Okay, next slide, please. And so I just kind of wanted to share some ground temperature data. I'll show you data from Bonanza Creek and in interior Alaska and Selawik in northwest Alaska. And the Bonanza site is an example of where we have talik persistently year after year, and the Selawik site is going to be an example of an intermittent talik site. And so in this graph here, we have year on the x-axis, the temperature on the y-axis, and we have ground temperature data from depths of 1.08, that's the blue line, and 0.67 meters, that's the orange line. And you can see through time that we have gradual warming at both of these depths. And at the start of, in 2012, both census were below freezing. And as we approach 2017 through 2018 and then through to 2021, we see that the ground is not freezing in the wintertime. And so we have taliks forming in the winters of 2017 to 2018, 2018 to 2019, 2019 to 2020, and this last winter also. Next slide, please. So here's an example of a site with slightly less consistent data record, but still valuable. So this is Selawik, which is in northwest Alaska, quite close to the continuous permafrost boundary. Again, we've got year along the x-axis, we've got temperature along the y-axis. And this is, you can see, at the Bonanza site, there was a very clear trend in warming, whereas Selawik, for the year preceding talik formation, we had quite deep freeze, quite a big freeze at our sensors for 2 meters and 0.8 meters. And then we had talik formation occurring, and then we had refreeze once again in the winter of 2019 to 2020. And so this is an example of a site where we have intermittent talik development happening. Next slide, please. So what is causing recent talik formation? Next slide. So talik development seems to be dependent on two key factors. So potential thaw, so the amount of thaw, the depth of thaw in summer. And this is dependent on thawing degree days, thermal conductivity of the ground, and ice content. And then winter freeze depth, which is due to a combination of freezing degree days at the surface. So this is the combination of the air temperature, freezing degree days of the air, and then snow depths, as snow acts to kind of insulate the ground. And then thermal conductivity and water content also. So basically, when thaw exceeds freeze, we get the talik forming. So if we think about that in terms of, summertime active layer deepening, if that, we reach a maximum depth at the end of the summer, and then winter freeze begins to happen. And if that freeze doesn't reach the depth at which the thaw did, then we have an unfrozen layer that persists through the winter time. And so this is where we have talik formation. Next slide, please. So looking a little more at what's been happening with these freezing degree days and thawing degree day values in Fairbanks and Nome, so kind of interior Alaska and northwest Alaska, we can see that at both locations we have an overall increase in winter warmth and summer warmth. So what this means is that we have deeper thaw in summer and shallower freeze in wintertime, which is a recipe for incomplete winter refreeze of summer thaw. Next slide, please. So we can combine this concept of a relationship between freeze and thaw depth and healthy permafrost system and talik formation into a schematic. And so you can see here on the left-hand side of this diagram where we have essentially on the y-axis we have time and the x-axis we have depth. So on the left-hand side we have what we would consider, a healthy permafrost system where we have freeze exceeds, potential freeze exceeds potential thaw depth. So the summer thaw is completely refrozen because winter freeze depth meets or exceeds the depth of summer thaw. And so we have permafrost underneath the active layer. And then we have a threshold where our winter freeze and summer thaw are equal. And as we cross this threshold and we have warmer summers and warmer winters, our freeze no longer meets the depth of summer thaw. And then we have talik initiation. And what this diagram doesn't do a good job of illustrating is something like the Selawik site where we have intermittent talik formation, but just to kind of simplify the process, we kind of decided that it would be better to kind of illustrate it in this way where, if you have consistent freeze being less than thaw, then we have talik development, and this thickens through time, and the top of the permafrost drops through time, and we can see that our seasonally frozen layer also kind of starts to thin as well as we kind of get less and less freeze during winter as climate change continues to cause warming. Next slide, please. So kind of taking this idea of potential freeze and potential thaw and thinking about it, as a way to infer talik formation. If we didn't have borehole data, we explored, whether potential thaw and potential freeze kind of aligned with what we've been observing at the Bonanza Creek site. So this is a combination of numerical modeling for using historical climate data, observed data from our boreholes, and then projected climate data with using the GIPL permafrost model. And so on the x-axis here, we have years, and on the y-axis, we have depth of potential freeze and potential thaw in meters. And so the red line is potential thaw. So you can think of this as how deep thaw goes to in the summertime. And so through time, you can see that this line is increasing. So the depth of thaw is increasing. And then the black lines are potential freeze. So how much freeze we get in the winter time. And this is decreasing through time. And when these two lines intersect and the red line exceeds the black line, we get talik formation. And so you'll notice that there are two black lines. So we have one black line that is potential freeze using observed snow conditions and projected snow conditions. And then we also have the dotted line, which shows potential freeze under low snow conditions. So at the moment, what we're basically observing is that talik formation is occurring, but a lot of the time it's dependent on a thick snow capping in that summer heat in the ground. And so when we have a low snow year, that heat can escape more rapidly. And so this kind of dotted line gives us a conservative estimate of when we would expect to see talik formation at sites. So when thaw and freeze depth intersects, talik formation begins. And as you can see, it can be messy and intermittent. And snow increases the rate of talik formation. So more snow is good for talik, and less snow is good for permafrost. Next slide. And so we can kind of think about these two lines intersecting as different thresholds. So we have our first threshold. Next slide. Adds a few more bits and pieces detail-wise. So our first threshold, where we have intermittent talik formation, but it's dependent on average to heavy snow conditions. And then we have our second threshold, where talik continues regardless of snow conditions. And so you can see that there are two areas that are shaded in yellow. So the first threshold, and back in the 1990s, there was a period of pretty heavy snowfall that potentially could have caused some initial talik formation at the Bonanza site. Our observation records don't go back this far, but it is likely that there would have been a talik that formed and then refroze. And then we have our current phase of talik formation at Bonanza. So talik will persist as long as we get average or above average snow conditions. But if we get very low snow years, that talik might refreeze. And then around 2035, our model projections suggest that our summer thaw will exceed the depth of winter freeze regardless of snow conditions. So this is at the Bonanza Creek site, which could probably be more broadly considered as kind of like boreal forest within the interior of Alaska. So quite a large area that it could apply to. Next slide, please. So another modeling exercise we did was to consider or to explore how talik thickness may increase through time, again for Bonanza Creek sites. We've used Bonanza partly because it's quite representative of a large area, but also because we have quite long observation records, so we can really calibrate the model well using those observations. So in this graph, you can see year along the bottom from 1970 to 2090. And then depth on the y-axis, so 0 through to minus 14 meters. And the thing to kind of focus on here are the three colored lines that depart from the seasonal thaw, seasonal freeze layer. So we have the red dotted line. So this is the bottom of the talik, and this is modeled using lower ice content, so 30% ice content. And the brown line in the middle is 50% ice, and the purple line at the top is 70% ice content. And you can see that by around 2100, sorry, I clipped off the last tick there, but we have a talik depth at Bonanza that reaches around 14 meters thickness, which is thick. That's a significant amount of permafrost thaw. So you can see that generally where there's less ice, we have faster talik formation as we'd expect, and more ice would mean we have slower talik formation. Okay, next slide, please. So in conclusion, taliks are not just for lakes. Other work recently has really emphasized, and I should have touched on this earlier, that we're seeing talik formation at sites where we have wildfire disturbance that's quite widespread. So talics, we're starting to understand that talik development is going to be much more widespread as we have an increase in wildfire. But now also, as we see, summer thaw is exceeding winter freeze depths, we're going to have that process be, lakes, wildfire sites, and also just kind of terrestrial areas, subaerial areas. So talik formation at our sites is occurring when potential thaw exceeds potential freeze. And in the discontinuous zone in Alaska, it's currently dependent on, I would say, I should have written heavy, but kind of average to heavy snowfall. So we're within the first threshold. But talik formation will eventually occur regardless of snow conditions. And the modeling for the Bonanza site suggests this will happen around 2035. And then modeling efforts on talik thickness suggest that in areas of black spruce like Bonanza Creek, talik could reach a thickness of around 14 meters by 2100. So next slide, please. And so, for discussion points, I would really, I'd like to, any feedback on the data would be great, but also, to kind of hear people's thoughts on potential impacts of this talik formation on, different elements of the landscape and ecosystem. So hydrology, is this going to result in drying at the surface? Is this going to cause increased fire potential? How is this going to impact nutrient cycling, plant growth? Would this cause a shift in species composition once we have taken talics? Obviously, something like species composition is also going to be impacted by changes in air temperature too. Could this impact slope stability? Within the Fairbanks area, interior Alaska area, where we have Yedema, there's massive ice buried depths under some Holocene thermal maximum thaw conformities. So we have huge Pleistocene ice wedges that are around 6 meters or so deep below what is currently the base of the active layer. So, this will, if talik continues to propagate at the rates that we've modeled, we'll be having some kind of delayed kind of thermokarst apocalypse potentially in areas with this thaw conformity that overlays massive ice also, which is kind of interesting to think about. And then also just thinking about how these talics might propagate across the landscape too. It's interesting to consider. So just some ideas for discussion. We don't have to hit these, but I just thought I'd throw that out there. And then the next slide is kind of a scribbly sketch of these kind of discussion points. Maybe we could leave this up while we have a chat about different aspects of this data. So thanks very much for listening.
Thanks, Louise. That was a very interesting presentation. And I know I have some questions, but I thought I would see if anyone else has any questions or comments. You can either raise your hand or type it in the chat. And I'll try to catch it because I can't see everybody at once.
Looks like we've got 2 raised hands, one from Liz and one from Joanne. So maybe Liz can go first.
Okay.
I just wanted to give a shout out to some really fantastic science communication. This presentation was super clear, and I'm not a permafrost scientist, and I think I understood all of it. So just really wanted to give you some words of appreciation for such a good and clear presentation.
Thanks, Liz.
Joanne?
Hi, yeah, no, I'd just like to echo that it was a really nice presentation. And then just like 2 questions. One of them you kind of touched on in your discussion points. The other one, maybe you know the answer, maybe you don't. So for the taliks, when they refreeze and there's the seasonally frozen layer in the winter, do you have a sense of whether or not they could potentially become anaerobic while they're frozen? I would imagine that when they initially freeze, when there's the initial refreezing, it would probably be aerobic just because of the exposure to the atmosphere. But is there potential that the seasonally frozen layer could form a barrier to oxygen and potentially it could become anaerobic? Like, what sort of temperature is there in the talik? Is there potentially enough microbial activity that it could consume the oxygen and become anaerobic? And then also just like for the hydrology, do you have a sense of potentially like how interconnected these taliks could be? Is there the potential for like subsurface transfer of water, transfer of nutrients into different regions, so laterally across the landscape during the winter with the formation of the taliks?
Yeah, two great questions. And I think actually, Joanne, you're probably much more qualified to answer the first question. So I think, yeah, depending. So right now the talik thickness we're observing is probably 20 to 30 centimeters. It's hard to tell so right now we're just inferring talik thickness from sensors that are at intermittent depth. So the diagrams I showed earlier with the two sensors, we have more sensors at each of these sites, but I just kind of stripped down the data so that it would be a little clearer. But so I guess it would kind of be a combination of microbial activity, nutrients available, and the thickness of that talik and how long they're kind of capped in for. Would that be, I think that off the top of my head, but I'm not an expert by any means on nutrient cycling or microbial activity, but that is something I've considered. And I think I do wonder whether anybody's seen evidence of like methane burps, you know, as these seasonally frozen layers intersect with taliks in the springtime.
It's entirely possible, or maybe like if they're thick enough, if the bottom part becomes anoxic, or then, you know, there's potentially also the oxidation of methane if the part of it's aerobic and part of it's anaerobic. I don't know. Interesting. I don't know the answer.
Yeah, really interesting. Yeah, I mean, I think we should. Yeah, it definitely warrants much more thought. And then with the hydrological interconnectivity, I think there's been a lot of work done in the Scotty Creek watershed in Canada by Quinton and his team, and they have observed an increase in hydrological connectivity in fens where they've observed talik formation occurring. So they have kind of a mosaic of peat plateaus and fens, and I think that could potentially occur at these sites in the interior. I mean, one of the limitations that we have is that, you know, we're using these single points to infer talik formation and the distribution of those taliks. We're not sure how extensive they are, you know, like spatially. I know Tom Douglas with the Army Corps of Engineers has done some work recently. He's been taking permafrost cores and using geophysical surveys to look at the extent of taliks more widely. And I think they're seeing that they are quite spread out, and they could kind of contribute to hydrological connectivity. And I would imagine that eventually that's inevitable. Yeah. And once that occurs and you have subsurface water movement, I would expect that would also exacerbate or it increase the rate of talik formation too, due to the transfer of heat through water movement.
Cool. Yeah, thanks. No, yeah, I don't know the answer to either of those, but yeah, I was just curious your thoughts.
Yeah, I mean, it'd be really cool to chat to you another time about the microbial activity in talik formation, actually, in light of your past work.
So I would definitely like to follow up on that. So
yeah, that'd be super cool.
Thanks. Anyone else? Sarah, if you want to go ahead.
Hi, Louise. Thanks for your talk. I thought it was really interesting. And I apologize ahead of time because I joined in a little late and maybe you addressed this early on. But I'm wondering about the specific geometry of these taliks you're anticipating. In a lot of my work, I think about horizontal versus vertical taliks. And I'm wondering, I feel like you've sort of addressed them as more of a three-dimensional phenomena. I'm just wondering sort of what these actually look like. And if you can speak to that some.
Right. Yeah. So kind of echoing the comment to Joanne, you know, that is a major limitation of this study is, you know, we're taking measurements and at discrete point locations, and so we can, you know, I think we can't really infer the lateral or the horizontal distribution of these taliks, although you know, more broadly, you know, we did a little bit of kind of back of the envelope calculations and compared the ground thermal regime of, you know, the black spruce forest ecotype to other vegetation types. And it does seem, you know, like this is one of the colder ecotypes. And so the distribution of these taliks on an interior Alaska scale is probably really quite widespread. But on a local scale, that would be really interesting to look into, maybe kind of doing like geophysical surveys or kind of more intense borehole installation at sites where we know that we have talik presence, to explore kind of the role of variations in microtopography and variations in organic layer thickness, proximity to you know, trees and shrubs. I think that would be kind of really worth looking into, or maybe also complementing that with kind of more detailed model sensitivity runs with the model as well. But yeah, so with your sites, these are water tract sites with taliks, or?
I've thought about them from the modeling perspective, you know, in Alaska or elsewhere, but I'm always with the modeling, you know, the model usually shows a horizontal talik, but, you know, we don't know what it actually looks like. So I was wondering if you had some good insight. I didn't. It's so hard.
Yeah, I don't, I'm sorry. Yeah, like our model is just, it's just kind of a point, yeah, it's not a spatially distributed model. This modeling run that we've worked on, but again, yeah, Tom Douglas. I think that Tom Douglas and colleagues have a paper coming out in the cryosphere that may be discussing kind of the spatial distribution of taliks in a bit more detail. They have a few sites in interior Alaska around Fairbanks too, and I think maybe it's in press right now. But
great, well, thanks
yeah.
again.
Sorry, sorry to not have more info on that. Yeah.
And Caitlin, if you want to go ahead.
Yeah, thanks, Miriam. Really nice talk, Louise. And just to piggyback off that topic, I see Jeff put a comment in the chat that the heterogeneity of ice distribution, so sort of pre-existing conditions, likely makes talik geometry very complicated, and that makes sense. And also, I thought it was really interesting and sort of elegant, the point that you made with your model run of the effect of the snow depth and sort of putting an edge on that envelope by considering the scenario where there's zero snow. But I also am interested in your thoughts as to the real world geometry being affected both by the pre-existing ice distribution, sort of the pre-existing condition of the permafrost underneath, and then also maybe the spatial heterogeneity of snow accumulation, or maybe this is an environment where snow accumulation is pretty consistent. But anyway, that was like a question / comment from a glaciologist who just loves to think about permafrost, and it was a great talk. And that's my question / comment concluded.
Yeah, thanks for that question, comment, and thanks to Jeff for pointing out that, yeah, ice distribution does make talik geometry quite complicated. I guess I'd add to that, you know, if we look back at the slide which shows the talik thickness through time with the different ice contents, this will only be a factor for a little while, and then our summer thaw will potentially be great enough that talik formation is going to occur no matter what the ice content is. And so I think right now talik geometry is very complicated, as Jeff points out, but in the next several decades it will become less so. Yeah, and you know, echoing this idea, you know, doing more high resolution studies, more spatially high resolution studies of looking at talik distribution. I mean, if there are any geophysicists who are on the call who are interested in doing some geophysical surveys, I think that would be one really great way to kind of explore the spatial distribution of taliks and their interconnectivity.
And I saw Catherine's hand up and then followed by Jeff, but I don't know if Jeff wanted to follow up on his comment that he posted in the chat first, perhaps. Sorry, Catherine, I don't mean to.
Maybe this is a good time. Yeah, maybe this is a good time to do that. Even given the fact that taliks will form regardless of ice content, they will have already started forming deeper and more where the ice content was less than.
Yeah.
So there's still going to be this geometric difference. And that's a huge deal for DOT from an infrastructure standpoint, because it's the differential settlement that tends to be our biggest problem, as opposed to overall thaw depth. So anyway.
Yeah. I mean, that's interesting to think about, because I think, especially around Fairbanks, where you have these massive ice wedges that are at depth, 6 to 10 meters depth below the surface. So you're going to have some areas that have massive ice close to the surface, where you'll get this initial wave of thermocast, and then you'll have these other areas around Fox. You'll have a bigger lag, and then the thermocast is going to be much more acute and deeper. So I think it's going to be, I agree. Yeah, it's going to be, I guess initially it'll be quite heterogeneous with regards to the thermocast development and the differential settlement that occurs due to this process. Yeah.
We actually have had some places where the ice distribution was homogeneous enough that we have roads that are a layer of asphalt, 6 inches of gravel, a layer of asphalt, 6 inches with 4 or 5 layers, and they're all relatively flat. All they're doing is accommodating this progression of settlement, but that's usually not the case around Fairbanks, and anywhere we have heterogeneous ice, then that's where we get the roller coaster.
What areas? Which areas are you getting this kind of all over lowering of the road?
That was, I think those photos were down on the Richardson Highway, much closer to Valdez, but it was not in Yetama territory.
Interesting.
Thanks.
Thank you.
Thanks, and we'll go to Catherine next.
Thank you for your talk, Louise, and I certainly want to echo Liz's statement about your talk being very accessible for those of us who are not specialists. My question is about extremes of weather, and we are certainly seeing that with climate change. We're seeing, regions that get, heavy rains or violent storms or droughts. My question is, do you foresee that with snow cover, which you've identified as a driver for talik formation? And if so, how will that inform or limit your ability to predict the effects of talik formation on the environment? You talked about coastal erosion and the effect of communities. How do you see extreme weather fitting into this?
Yeah, I mean, from a snow perspective, that's a great question. And having the timing of snowfall and having these heavy early winter snowstorms in interior Alaska can really have a huge impact on the winter ground temperature for the rest of the season. So I think while we're in this window that I illustrated in this plot, where we had the 2 thresholds and the yellow shaded area and then the gray shaded area, I think while we're in this initial kind of threshold 1, where talik formation is pretty dependent on snowfall, snow could really cause, it could retard talik formation if we have very late snow, very thin snow cover, or it could really speed up talik formation if we have very early snowfall that sticks and we have these thick dumps of snow that stick. Kind of linking this in with coastal communities, I mean, I think that talik formation, I think that this is on a tangent. I mean, I would imagine talik formation could potentially exacerbate the rate of coastal erosion as well. That's something that we haven't really looked into yet, but that's definitely worth considering. But yeah, so I don't know if I have too much more to say about extreme weather events, other than, the timing of snow and the thickness of snow is going to be really kind of a huge driver in the rate of talik formation in coming decades, until we have the second threshold where we have our summer thaw depths just so deep that it doesn't matter what the snow does. Yeah.
Okay, thank you very much.
And we have a question from Heidi.
Yeah, I was curious if you could speak at all to like the interaction between subsidence that is potentially happening in these areas of talik formation and snow depth. One of the things we've seen at our site is that we have seen these huge pits forming, there are taliks forming where we're warming permafrost, and with that, like the snow depth is always like at least as deep as that pit is deep, and so that's kind of, I think, speeding the rate of thaw. And so I was curious to hear your thoughts about what role that might play in talik formation.
Did we lose Louise? She's having some connectivity issues, so.
I see her here, but muted, maybe *6 to unmute.
She might try to call in.
Here she is again. Let's see.
Hi, can you guys hear me?
Yes.
Yeah.
Sorry.
Heidi, do you want to re-ask your question just in case Louise didn't hear you?
Yeah, sure thing. So I was just wondering if you could speak to the interaction between any subsidence that might be occurring in these areas of talik formation and snow depth, because we've seen like increased snow depth kind of occurring where we have subsidence at our site, and that seems to be speeding the rate of thaw. And so is that something that you've thought about at all, seen at all, you know, anything like that?
Can you guys hear me? Hear me okay?
Yes. Can you not hear us?
Can you guys hear me?
Yes, we can hear you.
Sorry. IT catastrophe. Yeah, that's a great question. So at most of these sites, surprisingly, we haven't actually seen too much thermokarst development yet. I think must just be that there's a lot of our sites are not located directly in areas of massive ice or ice wedge polygons, but I would say yes, you know, once thermokarst terrain does begin to develop, I would imagine these thermokarst low points would potentially be snow accumulation zones where we would have more of a bigger influence of snow kind of capping in that summer heat, and as a result of that, it would kind of exacerbate talik formation.
Thank you.
Do you guys have any taliks at the sites that you're observing thermokarst development at?
Yes, we do, but we actually saw thermokarst development prior to talik formation in our warming sites. And in our control sites, we are seeing some talik formation without major thermokarst development, but I have a feeling that is just a matter of a year or two at this point.
Yeah, I mean, what's interesting to think about is talik formation directly over areas where there is massive ice isn't really possible. So it would be the areas adjacent to massive ice. So if you have summer thaw depth, it's just going to intersect with ground ice, and then you would have subsidence over that area with ground ice, and you would just kind of basically your active layer thickness would be the overburden, and beneath that's ice, which would refreeze in the winter time. And so I think, you know, initially, until that ground ice is gone, we'll just have thermokarst, but adjacent, it'll be a very kind of, from a microtopography point of view, heterogeneous kind of process where you would have talik formation, say, kind of in between ice wedges occurring and in between massive ice bodies occurring, where you can actually have that deep summer thaw in the mineral material, and then in complete refreeze in the winter too. So that's kind of something interesting to think about also.
Yeah, thank you.
Thanks for that question. Yeah.
Anyone else have any lingering questions? We have about 4 minutes left. I'll just ask a quick question. You mentioned that one of your sites is at the Bonanza Creek LTER, and I'm assuming, since you mentioned it was black spruce, it's in the lowland area that has fairly thick peat deposits. I'm wondering what the role of the substrate of the soil or whatever is underneath plays in the, I guess, rate of talik formation or potential for talik formation to occur.
Yeah, I mean, the substrate is really important because it has pretty big implications for the thermal conductivity and how that heat, travels, how quickly the heat flux goes through to the mineral material beneath the peat layer, and then further and how that propagates downwards as well. So substrate is definitely important as with ice content too. But I think at the Bonanza site, it's kind of floodplain deposits, right? So it's kind of a mixed sandy silts.
Yeah. So I mean, I guess I don't know specifically where you are, but the cores that we have from the Bonanza Creek LTER are about 1.5 meters to 2 meters of peat, and beneath that gets, floodplain kind of.
Yeah, and this is something. Yeah, I need to. So it's interesting working with geophysicists because they're not interested. I looked back at the notes when they installed these sites initially back in like the 90s, and there's just like very little description of the thickness of peat and the composition of the soil. So I've been having to do some forensics, but I think next steps would be to kind of go to these sites and take permafrost cores and look at peat thickness and compare substrate type and peat thickness and how that plays a role in talik propagation. I think it's a really great point, and it's a super important component. And just kind of looking at whether talik formations are slower at sites with thicker peat or
and just I just thinking back of that figure of the temperature profile from the Selawik site. Is that also a black spruce site, or is that more of a?
No, that's a tundra site.
Okay.
Yeah.
And so I guess I'm just thinking about it in terms of the substrate. So potentially it's more responsive to temperature change interannually because it doesn't have like a lot of peat to buffer that.
Yeah, a thinner peat layer and potentially different substrate. I think around that area it's mostly kind of silt.
Mm-hmm. And then also at that site, I was curious about the role of sea ice. I guess that would just affect ground temperature overall, but yeah.
Yeah, I mean,
those comparisons to the sea ice event.
Probably affect snowfall too, right?
Mm-hmm. Yes.
Yeah. And potentially through time, we're going to see heavier snowfall at these more maritime locations as well.
Mm-hmm.
Yeah, I haven't looked into the relationship between sea ice decline in that area and snowfall, but I did see an interesting map Rick Toman put out the other day on Twitter that showed percent change in precipitation year-round for Alaska. And interior Alaska, there was not a statistically significant change in precipitation, but the North Slope around Dead Horse had seen, I think, maybe up to 30% more precipitation. But unfortunately, it was year-round, so I'm not sure whether it was winter or summer that was mostly contributing to that. But it seems like that potentially could be being driven by sea ice decline. And I'm not sure what Northwest Alaska looked like, but that's something I should go back and look at. But that's a great question. Yeah.
Well, thank you. This has been very interesting, and thanks everyone for the interesting discussion. It is now 3 o'clock, so we will adjourn the meeting unless anyone has any final parting thoughts.
Thanks for these great questions and comments. It's some really great ideas to think about.
Yeah, thank you so much, Louise.
Thanks all.
Bye, everyone.
Bye.